All right, let's begin. So the main objective for phase separation really is to discuss the chemical principles upon which simple distillation and fractional distillation are based, which is lovely Raoult's law, ideal solutions as well that are zeotrophic, as well as the positive and negative deviations from Raoult's law, which are azeotrophic in nature. Right? Main thing here is really the previous knowledge required, right? You need to know what evaporation is. And I'm not gonna insult anybody's intelligence by asking what it is, right? We need to know what vapor pressure is and boiling as well as partial pressure. Now, I might ask what partial pressure is, and I'm going to ask. So, could somebody explain to me what partial pressure is? What is partial pressure?
I think partial pressure is the pressure exerted by the vapor molecules only.
Huh. Interesting. I would define that as pressure, but not necessarily partial. Can you add the partial to it? Because what you're saying is that the pressure exerted by vapor or gas molecules, that is what pressure is. But what is partial pressure? Assuming I heard you right, you just find what pressure is, but I need to know what partial pressure is. Let's say that that gas is a mixture. What is partial pressure? We're talking about mixtures here now, guys. So what's partial pressure? Go ahead. Anyone? All right. Lovely. All right. Okay, so apparently somebody is giving the answers from the afterlife. Okay, so partial pressure itself speaks to the pressure exerted by one component of a mixture of gases. All right. So if you have a mixture of nitrogen and oxygen, the partial pressure of nitrogen, right, would basically be the amount of pressure that nitrogen exerts, right? And a partial pressure of oxygen would be the amount of pressure, right, or force that oxygen exerts on a container, right? So that's what partial pressures are. They speak to specific components of a mixture overall, right? And the overall mixture, right, the force that the overall mixture exerts on a container is what we call just generally a pressure, or what we call PT, or total pressure, right? So we have total pressure itself, and it's really a combination of all these different types of partial pressure and values of partial pressure. Okay, right? We know what vapor pressure is. Do we know what vapor pressure is? What is it?
So, I mentioned it earlier when I said that it's basically the pressure exerted by a vapor
Yes, that
in a
is what it
mixture.
is. Oh, that's what you were defining.
Yeah.
Oh, then yes. All right. So if you have a specific substance, right, that produces a vapor, the vapor pressure is the pressure exerted by that vapor. So it's really just self-explanatory like that. It's really simple. But we're gonna go through everything, right? And everybody should know what boiling and evaporation is, right? Not gonna insult anybody by asking that question, all right? So simple and fractional distillation. What we're looking at is what really underpins these, right? We know what simple distillation is, right? It's used to separate substances with two different boiling points, right? Right? Varying boiling points are far apart. That's fine. And fractional distillation is generally the same thing, but with multiple substances. So we have to look at the volatility of the different components as well as the boiling points of different components. Well, boiling point and volatility is relational, right? But we're basically gonna be separating, right, multiple substances, right, in which the vapor gets increasingly rich and more volatile, right, as we go up, right, the fractionating tower. All right, so that's it. So simple distillation is just two stuff. Fractional distillation is multiple stuff, right? For example, removing acetone from water, right? For simple distillation, for fractional distillation, cracking, right? of different types of hydrocarbons. Fine. All right. So key points now. Raoult's law states that the partial pressure of a component mixture, right, or a component in a mixture, equals the vapor pressure of the pure component multiplied by the mole fraction, right? An ideal mixture is one which obeys Raoult's law, right? That's one thing that is important. Boiling point, right? The composition curves for ideal mixtures can be drawn with which, right? Drawn which show a linear relationship between the composition and the boiling point. And boiling point composition curves, right, for non-linear mixtures may show positive or negative deviation. And that's what we're looking at, right? We're looking at what Raoult law is. We're looking at what an ideal and a non-ideal mixtures, all right? We're looking at what those are, right? We're looking at boiling point composition curves, how they relate with ideal mixtures, and the negative and positive delineation or deviation of non-ideal mixtures. Alright, so those are the things that we're looking at. Alright, so let's start. The vapor pressure, right? We know that solids or liquids or gases or anything like that, we know that liquids and gases in this case, right, exist in an equilibrium. If you have a bottle of water and you put the bottle of water down, right, there is going to be some amount of evaporation, right, within the liquid. So the water itself, some water molecules are going to break the surface tension of the liquid and actually exist, right, in its gaseous form within the part of the bottle that is air filled, right? And then the water molecules may condense, right, or be redissolved back into the overall solution, the overall water itself, right? So what we're saying here is that a vapor is produced, right, at equilibrium like that, right? So what I'm saying here is that if we have a bottle, right, with water in it, right, some molecules may break surface tension and some molecules may return to the substance, right? When these rates are roughly balanced, we enter a dynamic equilibrium, right? Topic 2, Module 2, Unit 1 Chemistry, right? Chemical equilibrium, right? But this is not chemical equilibrium itself, right? This is physical equilibrium. What we're looking at is a change in state of the same thing, right? So don't put chemical equilibrium, right? But it's physical equilibrium. It's a physical dynamic equilibrium, right? Within a closed system. We know that it must be at in a closed system at a given temperature, right? At a steady temperature. So that's one of the things that happens within a propane cylinder, right? In your kitchen at the moment, right? There is some amount of liquid in it, and then there's some amount of actual gas in it, right? So liquid doesn't actually spew through your stove, but the vapor, right, that is produced from the liquid propane, that is what is pushed into the stove, right? So the vapor pressure itself, this is the pressure exerted by the gas in dynamic equilibrium with a solid or liquid in a closed container at a given temperature. That is the full definition, right? So we're looking at that now, right? So Dalton's law of partial pressure, if we have a mixture of gases, what do? So it's a law that states that the total pressure exerted by a mixture of gases is equal to the sum of the partial pressures of the gases in the mixture. So if we were to look at if we put oxygen in a bottle, right, the total pressure exerted on the walls of the bottle must be equal to the partial pressure of oxygen, nitrogen, argon, right, all different types of chlorofluorocarbons, all different types of gaseous molecules that exist in the substance itself, in the mixture, right? We must account for each partial pressure, and then we take the sum of all the partial pressures to give us the total pressure, right, existing. But usually experimental, we usually know what total pressure is, and then we try to find the partial pressure of each gas that contributes to the total pressure. All right. Now, propane itself, we're looking at something that is relatively pure, right? But what happens for non-volatile substances? Propane is volatile. We should know that some of our alkanes, our short chain alkanes, are volatile. We should know that, right? So what about non-volatile solutes, right? In a volatile solvent, let's look at sodium chloride, which If we put sodium on a desk, it doesn't magically float away. It's not volatile, right? It doesn't evaporate easily, so it's not volatile, right? So if we put something non-volatile like sodium chloride into water, right? Raoult's law, right? We know that Raoult's law states that the pressure of the solution, right, or P of the solution, right, must be equal to the mole ratio times, right, the pressure of the solvent, right? So we're looking at this now. Partial pressure of the solvent, right? So let's look at this. The law states that a solvent's partial vapor pressure, right, in a solution or a mixture is equal or identical, doesn't have to be equal, but identical to the vapor pressure of the pure solvent multiplied by the mole fraction of the solution, right? So we look at the vapor pressure. P naught tends to speak to vapor pressure, right? But P itself speaks to partial pressure. So the notation is going to get increasingly weird, right? So P naught is vapor pressure, P itself is partial pressure, right? P is only expressed as pressure if it is P total, right? So we need to note that. So the law is there, the information is there, the mole fraction, right? Na over n total. The mole fraction is a unit of concentration defined to be equal to the number of moles of a component divided by the total moles of a solution. So if we have a solution of 10 moles and 5 of the moles, right, is nitrogen and the other 5 is oxygen, right, then the mole ratio, right, is going to be 1, right, upon, it would be actually 5 upon 10, right, which is 1 upon 2, right? So that's how the mole ratio works. The mole fraction rather works, right? So that's what it is, right? We look at the number of moles of one substance and we put it above the number of moles of everything in the solution or everything in the mixture. All right? So that's generally what we're looking at. These are the 4 main concepts that literally everything else in this entire PowerPoint builds off of. So if we don't understand something, this is the time to ask a question. Are there any questions or concerns, guys? Alright, just drop a 1 in the chat if everything is fine and we're ready to move on. And yet again, if there's a question, please ask. Alright, lovely. Raoult's law and vapor pressure. Now, the chemical principle of simple distillation and fractional distillation. That's all it is, right? But it is a bit. So Raoult's law now states that the vapor pressure of a solvent, right, above a solution, right? So the vapor pressure of the solvent, the dissolved solvent above a solution, is equal to the vapor pressure of the pure solvent at the same temperature, scaled by the mole fraction of the solvent present. P solution is equal to chi solvent, P naught solvent, right? That is after X, it's chi, right? For example, chi square test, right? Chi. Alright, so to understand the law, one should first understand vapor pressure, the pressure of a gas. So you need to understand that. I'm gonna leave you guys with that. That should be fine. Alright? So I'm restating Raoult's law over and over and over again. Alright? So let's look at this. Figure 1 on the right, right, shows 2 beakers, right? One containing a pure solvent in blue, right? And one containing a combination of a non-volatile solute and a pure solvent, creating a solution. Alright. For the pure volatile solvent A, the molecules evaporate from the surface and form a vapor. Fine, right? Eventually, an equilibrium is established in which the rate of the movement of the solvent molecules to and from the liquid are the same. Fine. So A in a liquid form is, you're gonna have 2 arrows, a double arrow, right? And then that would give us A in the gaseous form, right? So it's a dynamic physical equilibrium, alright? The pressure exerted by the vapor molecule is called the vapor pressure, and vapor pressure arises with temperature, varies with temperature rather, right? If we increase the temperature of a substance, we increase its rate at evaporation, right? So we increase the rate of evaporation. So if we're gonna actually increase the temperature of a substance itself, the vapor pressure will increase. If we decrease the temperature of a substance, the vapor pressure will decrease, right? Therefore, vapor pressure is directly proportional to temperature, All right. So if we're looking at that, the vapor pressure itself, let me just put um P itself, right? So this would be P naught, the vapor pressure is directly proportional to the temperature. Have the urge to write it in Kelvin, but I think it really doesn't matter. Change in temperature doesn't matter because it's gonna be the same thing with Kelvin or degrees Celsius or Fahrenheit. Alright. So it's gonna be directly proportional to change in temperature, alright? So that is what's happening here. So the pressure exerted by each component of the vapor alone is called the partial vapor pressure, right? So we have partial pressure and we have regular pressure, but now we have vapor pressure and partial vapor pressure, alright? So hopefully this makes sense, alright? If we're looking at oil, right? If we're looking at like a non-volatile solute, let's say this is sodium chloride oil or something like that, right? If we're gonna mix in something non-volatile, that will also decrease the vapor pressure. What will happen is that, let me just draw a little thing here. Let me erase that because I don't know what that was. All right. Let me use this for the explanation. All right. So if we have something containing a substance here, right? If we have non-volatile solute, right? Non-volatile solute speaks to the fact that it won't create a vapor, right? And we have volatile solute. Some of the volatile solute will be able to escape, but not all. Because the non-volatile solute itself, right, is gonna stop the evaporation. So what we're saying is that if we have a solute that is non-volatile dissolved into the solution, right, it may actually contribute to some higher surface tension. It may contribute to actually blocking the molecules, right, and reducing its chances of reaching the surface and actually evaporating, right? Evaporation only occurs at the surface of a liquid, right? So if your surface of a liquid have non-volatile solute there, then there's going to be less area or less chances for your volatile solvent to actually evaporate. Does that make sense? So it's going to be like it acts like a barrier. Like same thing where you actually put oil on top of a liquid, right? The oil is gonna stop the liquid itself from evaporating, then the oil is non-volatile, therefore vapor pressure will be greatly reduced. Alright? If you can't evaporate to create the vapor, then it doesn't make any sense. No vapor pressure will be produced, right? So as I'm saying again, if you have a non-volatile solute in a volatile solvent, right? The volatile solvent is the thing that should evaporate, right? And actually create our vapor. But if you have a non-volatile solute, right, it may actually stop some of the solvent from vaporizing, from evaporating, and produce less vapor, which will contribute to a smaller vapor pressure. Arifa, is that fine now?
There, someone's asking you to repeat.
Yeah, I'm asking her if she's fine. Thank you. All right. Lovely. So oil is a non-volatile liquid, right? Compared to water, right? So what happens when you mix oil with water? Will it affect the vapor pressure? As we stated before, yes, it will, right? So if we're gonna put the oil there, right? So let's say that the green solute, right, is the oil. If we're gonna put the oil above it, right, that will actually trap some of the water molecules in the oil layer, actually decreasing the number of water molecules in the vapor phase, right? So it's going to decrease the amount of molecules that can vaporize, therefore the amount of molecules in the vapor phase is actually decrease, right? So in here you have 8 water molecules here, right? 8 solvent molecules in a pure solvent. You're gonna have a lot of solvent, right? But if you mix it with a solute, you're gonna decrease the amount of solvent molecules, right? Therefore decreasing the vapor pressure. So if we plot this on a graph, right, between vapor pressure and mole fraction of the solvent, we'll find a linear relationship between them. When the mole fraction is equal to 1, it corresponds to a vapor pressure of a pure solvent, right? And a vapor pressure that vapor pressure, right, decreases linearly, right, up to 0 when the mole fraction equals 0, right? We're gonna look at that relationship, right? But what we're saying here is that if the mole fraction is 1, right, therefore the only pressure of the solution will be the vapor pressure, All right, hopefully you can see that mathematical relationship, right? And if the mole fraction is zero itself, right, the vapor pressure will decrease to be zero. So if you times something by zero, it's zero. If you times something by one, it is itself, right? So what? It's all dependent on the mole fraction. So if we plot that graph, right, it should look something. Well, I'm gonna show the graph, right? The graph is actually within the PowerPoint somewhere down, right? But it's gonna have that linear relationship, right? Let me have a look at this, right? So if you have a graph like this, right, let's say that this is a concentration of A, right, and this is a concentration of B, right? There's gonna be some amount of relationship between them in which you're gonna have an entire line, and as we approach the other, right, we're going to actually have decreased vapor pressure. So you're gonna end up with graphs that are kind of like this, right? And sometimes you're gonna have to draw the relationship between the highest point of A and the highest point of B. We're gonna get to all of that, right, in a little bit, right? We just have to understand the concepts first, and then we're gonna get to all of those different graphs and what they mean. All right, just bear with me a little bit and see if you can understand all relationships. All right, so we need to head here first before we get to any type of graph, right? So let's have a look at here. So Francois-Marie Raoult, right, said that the vapor pressure is a function of the mole fraction, right? So this is him on the side here, right? So he gave a relationship which is known as Raoult's law, right? So number one, right? Notice that this is all in numbers, right? So number one, if the mixture contains non-volatile solute in a volatile solvent, the pressure of the solution, right, is going to be directly proportional to the mole fraction of the solvent, right? So we're going to have that there, right? So the vapor pressure of the solution, the pressure of the solution itself, right, is going to be equal to the vapor pressure times mole fraction. When the mole fraction is 1, it's going to be basically the same. All right? That makes sense. So if we actually, well, let me not take it for granted. Everybody understands the first concept here? Does everybody understand the first concept here? All right, so it's here, right? If we have a mixture of a volatile solvent and a non-volatile solute, meaning a solvent that can easily evaporate versus a solute that can't, right? The relationship, right, that we speak about, Raoult's law, will state that the pressure of the solution itself, right, the pressure produced by a solution, right, will be the partial vapor pressure of the solvent, or the vapor pressure of the solvent in and of itself, right, times the mole fraction. But if the entire thing is pure, the mole fraction will just be 1/1, which is 1, right? So that will leave our mole fraction to be 1, right? So that would mean that the overall vapor pressure of the solution will just be equal to the vapor pressure of the solvent because it's pure. Does that make sense?
Not really, sir, honestly.
Okay.
Yeah.
Okay, all right. Hold on. All right. So, simple distillation. All right. Let's take a step back. All right, let me see if I can get a clear screen and work on it like that. All right, these slides have a weird thing to them. All right, so let's try this. Okay, all right. Okay. Do you guys understand things more graphically, like through graphs and stuff like that?
Sort of.
All right, so I'm gonna use a graph, right? I'm gonna use like 2 graphs, right, to have a look at this, okay? So let's say that, and these graphs have 2 y-axes, right? Please note that they have 2 y-axes. So you're gonna have 1 y-axis, right? Let's say that we have substance A that gives a partial pressure, vapor pressure, right, of A, all right? Fine, right? So you're gonna have that there. Everything should be fine there, right? So let's have this as A, and let's have this as, no, let's not actually have that as A and B. that would be more confusing. No, actually, I have to have A and B. Let's have this 0 here and 1 here. Right? Let's put this as A. Let's put this as B. Trying to remember how we draw these graphs. All right. Then you would have the partial pressure of B, right? Or in this case, the the vapor pressure, right? So let's get this then. So let's draw a graph looking like this. Let's get it something looking like this. All right. So if we're looking at something like this, right? That would be 0 AN. Let's look at in relation of A, right? The partial pressure of A. Okay. So note that this line is gonna be A here. So this line is gonna be A here. Alright, then I'll put the arrows on. Alright. Now when we're gonna start at 0, right? If we have the mole fraction, right? So down here is a mole fraction. Alright, and then you know the y-axis would be the actual pressure, alright? So let me just ask you guys, just give me a little bit of concentration to explain this, right? So the x-axis is the mole fraction, the y-axis are the partial pressures, right? So in relation to A only, we're looking at A, right? If we start here at the origin, there would be no pressure for A. Make sense? Because the mole fraction for A would be 0. That means that none of A exists. Following?
So can I read that one more time?
If the mole fraction for A is 0, that means that none of A exists, right? Meaning that the fraction of A in the solution is 0. Let me just do 1/2 first. Let me do 1/2 first. Let me fix that, all right? So let's focus on this. This makes more sense, all right? So as the mole fraction increases, right? Remember, it's a fraction. The highest value that you can get is 1, right? As the mole fraction increases to 1, right? A will continuously increase. So you know what this is? This is actually showing increase in concentration of A, right? As it relates to the partial pressure of A. So as we increase the amount of A, we increase the partial pressure of A. That makes sense, right?
Yes, sir.
Okay. So this is speaking about A as a pure substance, right? If we add something else to the solution, let's say B. Let's get the vapor pressure of B up here. Alright? Now, alright? Let's have a tiny look at what really is happening here. Alright? If we're gonna have a mixture, right? We're gonna have a relationship between the two mixtures, right? A and B. Alright? So let's have a look at this. This should actually be 0 now. So I'm changing up the graph a little bit. Here B would be 1. Here A would be 1. Alright? Now let me draw a relationship now for B. Alright, so let me just put circles on B. Alright? Now this would be B. What's happening now, if we're looking at this side of the graph now, right? For B, if B's origin is 0, if B's mole fraction is 0, right, that means that there will be no pressure of B. And as we increase going this way, right, we can see that the line goes up, right? That the partial pressure of B increases, right? Does that make sense? We're looking at two different sides of the graph. Does that make sense so far? We're just looking at B as itself. So B is on the right hand side, right? And the curve that is increasing in that way, right? To the left, right, that I put the circles on, that curve is B, right? So if the partial pressure of B here is gonna be 0, let me use the laser pointer. If it's gonna be 0 here, that means it's gonna be increasing with that relationship as we increase towards a mole ratio of 1. Does that make sense?
Yes, sir.
All right, so that's fine for now. All right. So what we're saying with relation to A, just follow the laser pointer, right? So with relation to A here, right? If the amount of A in the solution is 0, right? And we increase towards a mole fraction of 1, A will continuously increase in this direction. If we're looking at the pressure of B now, right? If the mole fraction of B is 0, that means that no amount of B is there, right? We're gonna have that pressure increasing as we move to a mole fraction rather of 1, right? So what we're looking at is two separate graphs now. We'll just put them together, right? But here's how the thing with the mixture comes in, right? The mole fraction would actually dictate how much of the substance is there, right? It's a purity, meaning that on the position graph over here, right? It would just be a pure solution of A and none of B. So over here on the right hand side, A's mole fraction is 1 and B's mole fraction is 0. That means that there's no B and it's all just A existing. Does that make sense?
I have to repeat that.
All right. What we're looking at on the right hand side of the graph is that on this area here, this origin over here, B's mole ratio is going to be 0, meaning that no substance B is present, right? But A's mole fraction is 1, right? So everything that is existing in this region is going to be A, so A is going to be pure. So as A approaches 1, right, as the mole fraction of A approaches 1, it's going to be pure, right? A, right? But as B approaches its 1 over here, right, it's going to be pure B alone, right? So what we're looking at is the fact that the mole fraction determines everything, right? Vapor pressure is a function of the mole fraction, right? So a mole fraction being 1 means that there's nothing but that substance present. A mole fraction of 0 means that substance is not present. So as we go through towards 1, a mole pressure of 0, nothing is there. A mole pressure of 0.5 means half of the solution is that substance. And a mole fraction of 1 means that the entire solution or the entire substance, right, is made up of one thing, right? That is kind of what he's saying here, right? He's saying that the partial pressure is a function of the mole fraction, right? So if we have no if we have no other substance itself, right, and there's only one thing present, that mole fraction will be 1, meaning that out of everything in the substance, it's only that thing exists, right? So what we're saying is that if we have a non-volatile solute in a solvent, right, that is going to be the relationship with it, right? So what we're saying here, let's say that A is the solute, right? So let's say that A is the solute and B is the solvent. All right? What we're going to say is that the overall pressure within this system, right? Usually denoted by that line. The overall pressure in the system is going to be equal to the mole fraction, right? Times the partial pressure. Or the vapor pressure, rather, right? So what we're seeing here, if we're going to be looking at this position around here that I just put the box on, right? This position here, right? If we're looking at the total pressure, right, of the system itself, right, for let's say A, right, here, the pressure of A will be 0 times the partial pressure, right, or the vapor pressure of A, which means that A does not exist. A exerts rather no pressure, right? At this area, the mole fraction is 0, right? Meaning that none of A exists, right? But if you're looking at over here, right, where the mole fraction is 1, right, the overall pressure of the system will be equal to 1 times the vapor pressure. Meaning that all the vapor pressure that exists, right, all the pressure that exists is from A. So meaning that the overall substance that exists in the entire solution will be A, right? But that is not how it works with mixtures. With mixtures, you're going to always have this weird graph present, right? And you're gonna have to look at it in relation to two separate substances. So what this guy is trying to say is that if you have a non-volatile solvent, right? Sorry, solute dissolved in a solvent, right? A volatile solvent. This is the relationship. The solution is directly proportional to the mole fraction, right, of the solvent itself, right? And the constant itself, right, will be generally the pressure at a specific point, right? So that would be the constant there. Give me one moment, Nicholas, for me to just finish this thought, right? So the overall pressure is gonna be equal to that vapor pressure times the mole fraction, right? Times basically the concentration of that thing in the substance, right? Because mole fraction is a type of concentration, right? So if there's only that substance, the mole fraction will be 1. Hence, right, the overall pressure will just be the vapor pressure of the substance, right? But if that mole fraction is actually different, right, then we're gonna actually account for that, right? Looking at the pressure due to only that type of vapor pressure in the substance, right? Or in the mixture. So what we're saying is that pressure is directly proportional, right, to the mole fraction of the solvent, right? So how much of the thing there, right? So if you think of it like this, right, the pressure of a gas A is proportional to how much of gas A exists, right? That's what it's saying, right? But the overall total pressure of a solution, right, itself will be the sum of the partial pressures, right? But if we're looking at the total pressure coming from one thing in the substance, right, we're gonna have to look at the vapor pressure of that substance times its mole fraction, right? And that's how you're gonna get the total pressure, right, or the partial pressure of that one thing within the solution, right? It takes a lot to really get to understand it, right? I'm not sure if there are better ways to really explain this, but that's what it generally is, right? As we approach 1, we approach 100% of the thing in the solution, pure solvent, right? As we approach 0, then the amount of solvent is decreased. If it's 0, then there's no solvent, right? So honestly, if it's only a pure solution, right, the partial pressure will be equal to the vapor pressure. That is what it's saying, because only that exists. Does number 1 make sense for simple distillation so far? If only something exists, right? If mole fraction is 1, if only that thing exists, right, then the total pressure must be the vapor pressure that only that thing exerts, right? Because it will just be only that. So if you have a water bottle, right, pure water, right, the mole fraction of water would be 1 because nothing else exists, right? Remember, the mole fraction itself is the amount of moles of the substance that you're looking at divided by the total number of moles, right? If it's only water, it's going to be 1 over 1, right? It's going to be whatever mole of water over whatever mole of water. So let's say in your water bottle you have 6 moles of water and it's only water. The mole fraction is going to be the 6 moles of water over the total number of moles, which is 6, because it's only 6 moles of water exists. Therefore, the mole fraction will be 1. And that speaks to the fact that all the vapor exerted by the water, right, itself, that will be the vapor pressure, right? And the total pressure of the system will be equal to the vapor pressure times 1, because it's only that substance exists. Therefore, what we're saying is that the total pressure, the partial pressure of the thing will be equal to the vapor pressure if only that thing exists in the solution. Does that make more sense? That was a lot of
Sense.
Makes more sense now. Nicholas, you were saying something. Go ahead.
Oh, yes, sir. I was just saying I just came in and I would like to go over it, but you went over it. Also, this guy kind of looks like Karl Marx if he had a good haircut.
Whoa. Friend summary Raoult. Alright. I guess so. All right, but I'm hoping that everybody gets that, because you can't have the total pressure of a system has to be the pressure of exerted by the only thing there, right? If you had a mixture now, it's gonna be different. So what one here is telling us, right, is that if only something exists, if only that thing exists, the total pressure is only the pressure exerted by that thing, right? So if you have a solution with, if you have a container with A, the only thing contributing the pressure is A, right? That's because you have a mixture of a non-volatile solute and a volatile solvent, meaning that the non-volatile solute is not going to contribute to the vapor pressure because it's not volatile. It's not going to evaporate. So it's only the solvent will contribute to the vapor pressure, right? And in this case, the partial pressure will be equal to the vapor pressure. Now, if we look at two volatile liquids now, pentane and water, right? We're looking at liquid-liquid extractions now. This is the theory that goes under that, right? We'll have a vapor pressure contributing from both of these, because both of them are gonna be volatile, right? That means that the vapor pressure itself, right, is gonna be made up of pentane and water, because both of these things will be evaporating. Now we're gonna have to look at Raoult's law in accordance with the mole fraction, right? So if we have a solution A, we're going to have to take the vapor pressure of that solution, right, times the mole fraction, right, the fraction of that solution that exists, right, the amount of things that exist there, right? We're gonna times them together to get the overall partial pressure of A, right? And then for B now, we're gonna take the vapor pressure of the water itself, times it by how much water there, and we're going to get the partial pressure of B, or water in that case, right? And how we get the overall pressure is through Dalton's law. The total pressure is going to be equal to the partial pressure of A plus the partial pressure of B, right? So what we're saying, if we have a non-volatile solute and a volatile solvent, only the volatile solvent is going to be contributing. Therefore, the total pressure is the pressure of the volatile solvent. If we have a mixture of two volatile liquids now, right, the two volatile liquids will be evaporating. So the overall pressure of the substance will be the total, or the sum of the partial pressure of the one substance, right, and the partial pressure of the other substance, right? That is what we're saying. Are there any issues or concerns so far? If there's a question, please ask. We're going to get this done right now. So if there are any questions, ask. Doesn't matter how long it takes, as long as every single person understands. Alright, just drop a 1 in the chat if you're ready to continue. Go ahead.
So, sir, this explains like how we're doing fractional of this simple distillation. This
No, we're looking at
works.
Oh, so explanation 1 is for simple and explanation 2 is for fractional. So the one that we just did is fractional, yes. It explains how fractional distillation works. Because as you move up the fractionating tower, the mole fraction is different. It's fractional distillation. So it's something like that. Alright? Hopefully this makes sense. Can you guys just drop a 1 in the chat if you were understanding and you're ready to move on? If not, please ask a question. Are we ready to move on? If you're not ready, ask the question, you know. If you don't ask a
Sir,
question.
can you give like a decent definition of partial pressure again? Sorry.
Partial pressure. You weren't here. Alright, so partial pressure itself, right? Oh, partial pressure definition is actually not in here. Alright, so partial pressure speaks to the pressure exerted by one component of a mixture, right? And you know, when we talk about pressure, we're talking about gases. So I don't have to tell you that it's gases, right? So it's the amount, it's the pressure itself, right, that is exerted from one component of the gas. So if you have a mixture like air, or actually, if you have a mixture like this that we're seeing here under fractional distillation, pentane and water, right? Where the total pressure itself is going to be the amount of pressure that pentane itself exerts and the total pressure that water itself exerts, right? So the partial pressure is going to be the pressure of each component, and the total pressure will be the sum of the partial pressures. Make sense?
Yes, sir, that makes sense. But then why could you like say in a vacuum that like a certain gas has a certain partial pressure? Wouldn't it always have to be in terms of something else, like a ratio?
It tends to be in a ratio, right? But this in this case, it wouldn't generally be a vacuum. It would just be that the space it exists in is only itself, right? Um, but you're saying that the partial pressure. Why we? Okay. The question is why I say it like it's in a vacuum, meaning only the gas itself.
Yeah, because like certain gases have their own partial pressures. Wouldn't they have a different partial pressure depending on what the other gases are or what the other fluids are?
Not necessarily for what we're doing here. So in case of what we're doing here, not necessarily. It will change. Pressure changes. The pressure laws. Wait, hold on. You did Charles' law, Boyle's law, and the Gay-Lussac law.
Well, yes, sir. I know
All
that
right.
is like this is only for ideal gases, but
We're looking at
I
them
see that.
in terms of ideal. All right. Okay, so this is what we're doing here. Most of our equations are based on ideal gases. All right. So only two persons drop a one in the chat. So three persons rather. I'm gonna assume that everybody's doing fine so far, and we're just gonna move on in case of time. All right. So Raoult's law, right? A mixture is an ideal solution if it obeys this law. We need to remember that. And there's the law there, and the law will show up over and over again, and I will continue to show the law over and over again. All right. So in 1886, the French chemist Francois-Marie Raoult observed that the partial pressure of a solvent over a solution of a non-electrolyte solute depends on the mole fraction of solvent in solution, right? So if we consider a solution A and a non-electrolyte B, right, in which be solid, it would be volatile or non-volatile, right? So it may be volatile or non-volatile itself, right? What we're saying is that according to Raoult's law, the partial pressure of A, so PA, right, over a solution will be equal to the vapor pressure of the pure solvent, right, which would be P naught A. Remember that P naught is the vapor pressure, right, multiplied by the mole fraction of the solvent, which would be chi A in a solution, right? So remember, that's all it's really saying. All right, that's all it's really saying. So the law is up here. That's all it's really saying. So the vapor pressure of a solution is equal to the vapor pressure of the pure solvent, right, times the mole fraction. I must be at the same temperature, right? Because we spoke about ideal conditions already, right? So it must be at that temperature, and we times it by the mole fraction itself, right? So if you're gonna have multiple stuff, right, that can actually evaporate, then it's gonna change the fraction. If not, the fraction is gonna be 1, right? All liquid mixtures deviate to a greater or less extent from Raoult's law, right? All of them. This is in ideal conditions, right? So those that more or less deviate, right, are called zeotrophic mixtures, right? So zeo meaning to boil and trophic meaning state, right? So more or less, if you deviate, you can have zeotrophic mixtures, and you're gonna have the formation of some azeotrophic mixtures as well. All right. So let's have a look at this. A mixture that is in an ideal solution. All right. Raoult's law establishes a linear relationship between vapor pressure and the mole fraction of a solute dissolved in it. According to this law, partial pressure of each component in a solution is the measure of its tendency to escape from the solution, and it's directly proportional to the number of molecules of that component present in the solution. All right, this is just restating the law over and over again in different ways. A solution which follows Raoult's law at all temperatures is called an ideal solution, right? Whether a solution is ideal or not depends on its molecules and its intermolecular interactions, right? So we need to go back to module 1, unit 1 chemistry. We need to know those intermolecular interactions, right? It's important to understand, right, what an ideal solution is and what makes it ideal, right? So an ideal solution, as we stated, right, is a solution in which the molecules of each component placed in a similar environment behave as they would if they were in a pure solution, right? So what we're saying is that if the molecules exist in an environment with ideal conditions, right, and they interact as if there's nothing else present, that is what an ideal solution is, right? So they're gonna have the same conditions, right, having no enthalpy and no entropy change. This is what an exactly ideal solution is. All right. This is only possible when molecules of both components are so similar in nature that they will interact in the similar way as if they were in their pure form, right? So what we're saying is that two separate things existing together behaving like they were alone, right? With no enthalpy change and no entropy change. This is what an ideal solution is. All right. So no heat would evolve when or absorbed as similar bonds are broken or formed, right? None of that will take place, right? And for the same reason, no change in entropy will occur. So obviously this is somewhat impossible, right? This is somewhat impossible in and of itself, right? So we're looking at this. So it's one substance. It's behaving as if there's only one substance exists, all right? So non-volatile liquid and pure solvents, right? So let's have a look at this, right? Going back to this simple definition, this simple diagram, rather, right? So we know that Raoult say that if we have a non-volatile liquid, right, to a pure solvent itself, right, there will be a decrease in the vapor pressure of the solvent. We spoke about this because it's gonna act as if it's blocking the volatile solvent from actually evaporating, right? And we speak of it's saying it here again, right? This is because corroding at the surface of the solution, right, kind of blocks that evaporation, right? It prevents the vapor pressure from actually increasing, right? It prevents that evaporation from taking place, okay? Right, that's what happens if we have a non-volatile liquid like oil and water. Remember that, all right? Therefore, when a non-volatile solute is dissolved in a pure solvent, the vapor pressure will be lowered, right? So it's same thing. So if a non-volatile liquid is going into the solvent, or if you have a non-volatile solute, right, which is usually a solid component dissolving, right, it's going to be the same thing, right? It's going to have the same effect. It's going to lower the vapor pressure, right? So if the solute is non-volatile, right, the partial pressure of the solution, right, is the total vapor pressure of the solution, right? Because the mole fraction of the solution is always less than 1, right? So it's going to be always less. Wait. The vapor pressure of the solution of a non-volatile solute is less than the pure solvent, right? So if we're looking at the non-volatile solute, it's going to be always less than 1, right? So we need to note that. Does that make sense? If we're going to have something that's volatile and only it can evaporate, right, then therefore, right, that only pressure that is exerted, right, that vapor pressure that is only exerting, right, will be the overall pressure of the solution, right? But if you have a non-volatile solute, right, or something like that that goes into a substance itself, right, if it is going to be producing a vapor pressure, right, it's going to have a lower vapor pressure, right? It's going to be different, right? It's going to be always, its mole fraction is going to always be less than 1 because it is not pure there, right? So we can have a look at some of these things, right? There are going to be a lot of graphs that we're going to have to look at to understand these concepts. Because I note that with a lot of the written information, it's not really grabbing on, but with the graphical information, it should be a little bit better, all right? We have a lot of graphs to look at, and we're gonna be looking at them now. All right, this was just the content relating to the law. All right, so here's a question here. So if you guys could screenshot it and answer the question, send the answer to me in the WhatsApp group, that would be lovely. Have a go at this question. 80 grams of sucrose was dissolved in 100 mils of water. What is the expected vapor pressure of the solution at 25 degrees Celsius? Alright? It looks as if it has too little information, but there's enough information here to do this question. Alright? And yes, these questions are purposefully a little bit more tricky than cave questions. Alright? But more or less it's simple. So you can have a go at that, but let's continue trying to understand the concept here. So I think understanding the concept is a little bit better when we apply Raoult's law to see actually how does this thing work, and probably how, after you see how it works, it will make a little bit more sense. Right, so let's look at this graph here, right, with ethanol here. So at 200 degrees Celsius, the vapor pressure of ethanol solute in water, which is a solvent, are, right, at 5.8 kilopascals and 2.3 kilopascals respectively, right? Calculate the vapor pressure of the mixture, the total vapor pressure, right, containing 0.1 moles of ethanol and 0.8 moles of water. Now this makes sense. The vapor pressure of the solution is going to be equal to, or the partial pressure of the solution rather, is going to be equal to the mole fraction of the solvent times the vapor pressure of water plus the mole fraction of the solute times the vapor pressure of ethanol. Why are they different like that? Because ethanol is a solute and water is a solvent. Alright? We note that the mole fraction here now, right, is going to be a little bit different. Note that we have 8 moles of water and 8 moles of ethanol, right? Therefore, we have 0.4 moles of water and 0.8 moles of ethanol, right? In order to get the mole fraction of our solvent, we must get the mole of the solvent over the total moles of everything in the solution. The solvent is 0.8, right? So if we do that, we must get 2/3. That's the mole fraction that we're going to times the pressure by, right? And then the same thing for the solute here. The solute would give us this mole fraction. All right. So if we do that now and look at the graph and times by the different pressures that we see on the graph, we should be able to get this, right? The pressure is actually provided in the question, right? So the solvent is gonna be, right, at 2.3 kilopascals. So we times that by 2.3, right? And the solute is going to be 5.8 kilopascals, so we times that by 5.8, and we're going to get everything over here. The total pressure is going to be 3.5 kilopascals. All right, so that's how you really do the questions. All right, so we get the mole fraction and we times it by the vapor pressure, right? In this case, it would be the partial vapor pressure, yes, right? So it's going to be timesing by that pressure there, right? And in order to get the total, we just add every single pressure together that we get. All right? Does this make sense? Does anybody have an issue with this?
No, sir. Can you...
Repeat?
No, sir. That makes sense to me. I don't think I was paying attention. Can you do it again, please?
Okay, so just explain again. So what we're basically doing, we're looking at Raoult's law, right? That states that Raoult's law itself, the pressure is directly proportional to the mole ratio, the mole fraction rather, right? That means that the pressure is going to be equal to the vapor pressure, right? Times the mole fraction, right? So that's what we're going to do in order to get the pressure of each substance. So we have our pressures here, right? And we have our number of moles here. What we're going to do to get the mole fraction is we're going to take, let's say that we're looking for the number of moles of water. We're going to put that over the total number of moles that exist, right? So it's always the number of moles of one substance, right, over the total number of moles that exist. So it's going to be like this, right? We're going to get that mole fraction. We're going to times it by the pressure provided to us in order to get the general pressures that we have here, right? In order to get P total, all we do is add each individual pressure to get P total, or P of solution. All right, that's basically it. Hopefully that makes sense. And notice how the pressure increases as the mole fraction approaches 1. Right? So we have that there. As everything approaches 1, the pressure will increase. Right? So we have that there. Now for ideal mixture of two components, right, A and B, let's say hexane and heptane, right, the theoretical vapor pressure is given up here, right? So we know what P total is, right? P total will be the sum of the two, and this is just expanding it to see how you get PA specifically and PB specifically, right? So this would be PA, and this would be PB over here, all right? So mixture from ideal solutions, right? They form ideal solutions if the intermolecular forces between the molecules in the mixture are similar to those in the pure substances, right? So meaning they form weak bonds, right? And there is no enthalpy or volume changes on mixing. So if there is no enthalpy or volume changes on mixing, and they're really, really similar, such that all intermolecular forces are weak, then we're gonna have an ideal solution, right? So we have that there. That should be more or less fine. So let's look at the effect of Raoult's law on the ideal solution. So here we have heptane and hexane, right? Looking at something like this. So on the figure here, right, we can see how Raoult's law really affects hexane and heptane in solutions here at this fixed temperature of 25 degrees Celsius, right? 298, right, Kelvin. Okay, as the mole fraction of the more volatile component increases, hexane increases, right? The partial pressure of the more volatile component increases, and the partial pressure of the less volatile component this decreases. So if we're looking at this, right? So looking at this, so they put it, the mole fraction of heptane is on the top, the mole fraction of hexane is on the bottom. Let me get the laser points, all right? So if you're looking at the hexane first, looking at the green, right? So first, the mole fraction is 0, meaning that no hexane is there. Therefore, there's gonna be no contribution of any type of pressure, right? So as we increase the amount of hexane in solution, the pressure exerted by hexane goes up, right? And if the mole fraction is 1, that means only hexane is here, right? Notice as the mole fraction of hexane is 1, the mole fraction of heptane is 0, right? And looking at the red line now, as we move towards 1 up here, right, the vapor pressure of heptane will increase. All right. So as one approaches, as hexane approaches 1, heptane approaches 0, and as heptane approaches 1, hexane approaches 0. So it's a fraction of how many things are in solution. If we have a mole fraction of 1, only it exists. If we have a mole fraction of 5, half of the solution is hexane, right, in this case, right? So if we have a mole fraction of 0.2, right, that means that 0.8 of the solution, right, is heptane. So it's relational like that. So as one mole fraction increases, the other mole fraction decreases, right? All try to approach 1, right, which is pure. So once we look at something like this now at 25 degrees Celsius, the fraction, right, of heptane, right, when it's at 1, right, when it's pure heptane, we're gonna have around 40 torrs, right, because this is using torrs here, so this pressure is gonna be 40 around here, and for the hexane it's gonna be around 100. So P total will be generally this line here, right? So we're gonna have that there. Generally this straight line here. So when you move up to higher chemistry, then we're gonna use calculus to find all sort of stuff. But in this case, we just use a simple relationship between them, right? That the P total is gonna be the pressure of hexane and the pressure of heptane. So that should give you generally our gradient here, right? Our P total. I'm wondering now, is this graph helping you guys to understand the concept relating to two solvents now? Does this make more sense? Does this help?
Yeah, sir, I think it does.
All right. Okay, where the lines cross doesn't indeed make it the mixture, right? As long as the vapor pressure, as long as the mole fractions of heptane and hexane are not zero, then it is a mixture, right? Where it crosses over now, all right, we're gonna look at that. We're gonna look at the formation of an azeotrope. We're gonna look at what's happening there. All right, we're gonna have a look. So hopefully this makes a lot of sense. All right. So moving on now, the effect of Raoult's law on an ideal thing. So we're looking at only one thing now. Let's look at this. Right, this makes a lot of sense as well. To measure the vapor pressure experimentally, it is difficult. So oftentimes, right, boiling point is used to measure the vapor pressure composition graphs, right? So it's used to mirror rather vapor pressure composition graphs, right? So we increase the boiling point, right, of hexane by itself, and we increase the boiling point of heptane by itself, and then we draw the graphs from there, right? So we treat one y-axis as one and the other axis as a y-axis as the other, right? So looking as we go across, now we can see that for hexane, remember the graph above, the hexane, the mole fraction, if it is 0, then there is 0% hexane in the solution. If it approaches 1, there's 100% hexane, right? Same thing for heptane. So if there's 100% hexane, then there is no heptane, right? 0% heptane. If there's 0% hexane, then there's 100% heptane, right? So in this case now, we're looking at, right, the both of them, right? So we're gonna have a graph that looks like this. Let me just draw this. It's gonna look weird because this is on a computer, of course. It comes from this, right? The line that we draw from the two ends, that is where we're going to get that entire thing there. So usually you're gonna have all these lines connecting. That line, that blue line that we draw from there, that is what we want. That is what we care about with boiling point composition curves. All right, that linear relationship between the composition and the boiling point, right? Composition means how much of hexane and heptane exists there. The composition of the mixture, right? And the boiling point. As boiling point changes, right? How does the composition of the mixture changes? So as we increase the temperature, right, we tend to have more hexane and less heptane. We're not gonna get into all of that yet, right? Right, but it's gonna have a different relationship to it, right? As we increase the boiling point, how does the boiling point actually changes in relation to the composition, right? That's what the graph is telling us, or trying to help us explain. All right. So non-ideal mixtures now. Some mixtures do not obey Raoult's law like this. So we say that they deviate from Raoult's law. So the deviations can be positive or negative, right? So there is not a linear relationship between the vapor pressure or the boiling point and composition, right? Meaning that we're not gonna get graphs that look like this. We're not. If it's linear like this, it obeys Raoult's law. If it does not, right, then obviously it doesn't. It's not ideal, right? It's not ideal at all. So only ideal solutions create this straight linear relationship, okay? So what happens if it's not? So let's look at positive deviations. If the total pressure is larger than the total pressure solution is larger than the ideal solution itself, right? Then it's going to be a positive deviation, meaning it's going to be endothermic. Examples of these is methanol and hexane or ethanol and cyclohexane. Yeah, we're going to look at that. We're going to look at how the graph looks, right? For negative deviations now, what we're seeing is that the total pressure of the solution is going to be less than that of the ideal counterpart. So we're relating it to an ideal solution. In this case, it's going to be exothermic, and an example would be ethyl ethanoate and trichloromethane, or we're going to have methanol and water. If we put methanol and water together, we're going to feel a little bit of heat, right? And that will tell us that this is not an ideal solution. Because remember, if there's any type of heat change, it's not an ideal solution at all. No. And the pressure of the solution is the pressure of the solution is greater than that of an ideal solution, right? It is going to be positive deviation, right? If it is less than that of an ideal solution, right, it's going to be a negative deviation. If they are equal, there's no enthalpy change, right? And that would mean that it is ideal. All right. Hoping that everything is okay. All right. So let us move onwards. All right. Are there any questions or concerns before we move onwards, though? Any issues before we move onwards? All right. I'm not hearing any and I'm not seeing any in the chat. Let's move. Right. Because now we're going to phase separations, the azeotrophs now, we're going to get into positive and negative deviations. Right. So hopefully Raoult's law makes enough sense, right, for us to get through everything like that, right? Are there any questions or concerns, guys?